Welcome to the fascinating world of non-chordates. Imagine walking into a massive, chaotic library where millions of books are dumped in a giant pile on the floor. If you wanted to find a specific book about marine biology, it would take you a lifetime. Biologists face a similar problem with over 1 million different animal species. Today, we are going to learn about the basis of classification, the brilliant sorting system that brings order to this incredible diversity of life on Earth. Now that we understand the sheer scale of animal diversity, let us look at why classifying them is so important. Understanding the basis of classification is absolutely critical because it provides the evolutionary roadmap of life on our planet. Without this system, biology would just be an endless, unorganized list of animal descriptions with no logical connection. By classifying animals based on their body plans, we can predict the biological characteristics, behaviors, and even the medical importance of newly discovered species. For instance, knowing the exact classification of a new parasitic worm helps scientists develop targeted drugs that exploit its specific biological weaknesses. Building on the importance of this sorting system, let us explore the actual rules we use to sort these animals. For non-chordates, we look at several specific criteria to determine their evolutionary relationships. The first is the level of organization, telling us if the animal is made of loose cells, organized tissues, or complex organ systems. Next is body symmetry, describing whether the body can be divided radially or bilaterally. We also examine the number of embryonic germ layers, classifying them as diploblastic or triploblastic. Finally, a crucial defining feature is the coelom, which is the internal fluid-filled body cavity that houses organs. Having identified the coelom as a key criterion, let us understand the physical reasons why some animals have one and others do not. To truly understand why animals are classified by features like the presence or absence of a coelom, we have to look at the physics of how they survive. Every single cell in an animal's body needs oxygen and nutrients, which must diffuse across the animal's surface. The relationship between the outer surface available for this exchange and the internal space that needs the resources is governed by a specific mathematical relationship. This dictates whether an animal can survive as a solid block of tissue or if it requires hollow cavities. This physical requirement leads us directly to the mathematical formula that governs animal body plans. The formula is R equals S divided by V. Conceptually, this ratio dictates how efficiently an organism can exchange materials with its environment. The variable S stands for the total surface area of the organism, representing the outer skin available for oxygen to enter. The variable V represents the total internal volume, which is the living tissue that constantly consumes energy. When the volume increases, the ratio R decreases rapidly. This means the animal has less surface area available to support its massive internal volume, forcing larger animals to develop internal transport systems. Now that we have our formula, let us see this with a concrete example by calculating the ratio for a simple spherical creature. We are given organism A, a sphere with a radius of 2 millimeters. We need to find its surface area to volume ratio. First, we use the geometric formula for the surface area of a sphere, plugging in our radius to get approximately 50.24 square millimeters. Next, we calculate the volume using the standard sphere formula, resulting in 33.49 cubic millimeters. Finally, dividing the area by the volume gives us a ratio of 1.5 inverse millimeters. Physically, this is a very low ratio, meaning simple diffusion is highly inefficient for the cells deep inside. Having seen how inefficient a spherical shape is, let us prove mathematically why a flatworm can survive without a coelom. We will model organism B, a flatworm from the phylum Platyhelminthes, as a thin rectangular box. Its length and width are 10 millimeters, but its thickness is a mere 0.1 millimeters. We set out to find its surface area using the formula for a rectangular prism. By plugging in these dimensions, we calculate a massive surface area of 204 square millimeters. The mathematical reasoning here shows that this flat shape acts like a giant biological solar panel, maximizing the area available to catch oxygen from the environment. Continuing our derivation, we now calculate the internal volume of this flatworm to find its final ratio. We multiply the length, width, and thickness, which gives us a volume of just 10 cubic millimeters. Despite being wide and long, its extreme thinness keeps the internal tissue volume very low. Dividing the surface area by this volume yields a ratio of 20.4 inverse millimeters. This mathematically proves our concept. The flatworm has a ratio more than 13 times larger than the spherical organism. This brilliant evolutionary solution provides such massive surface area that oxygen easily diffuses to every cell, completely eliminating the need for a coelom. So, we have proven that a flat body plan works perfectly for simple animals. This brings us to the challenge faced by thicker, more complex animals. As animals evolved to become thicker, simple diffusion was no longer enough. There is a strict physical limit to how far and how fast oxygen can travel through biological tissue. If an animal grows too thick, the cells located deep in the center will suffocate and die before oxygen can reach them. This physical limitation is exactly what forced the evolutionary development of the coelom, making it a major basis of classification for higher non-chordates. To understand exactly when diffusion fails, we rely on the one-dimensional diffusion time approximation formula. Conceptually, this formula tells us how long it takes for a molecule to travel a certain distance through tissue. The variable t represents the time in seconds. The variable x represents the maximum distance the molecule must travel, which we use as the total thickness of the organism. Finally, d is the diffusion coefficient, representing how easily the molecule moves through biological tissue. Notice that the distance x is squared. This means that if the thickness increases even slightly, the time required for diffusion increases exponentially, drastically changing the physical reality for the animal. Now that we have our diffusion formula, let us apply it to a small, solid-bodied acoelomate. We are given an organism that is 1 millimeter thick, and the diffusion coefficient for oxygen in tissue is 0.001 square millimeters per second. We want to find out how long it takes for oxygen to reach its center. We plug our values into the formula, squaring the 1 and dividing by 2 times the diffusion coefficient. This gives us a final answer of 500 seconds, or about 8.3 minutes. Physically, while this is somewhat slow, it is completely manageable for a very low-energy, simple creature to survive. Having seen that a 1 millimeter organism survives just fine, let us prove what happens when an organism grows thicker. We will calculate the diffusion time for a larger solid organism that is 4 millimeters thick using the same diffusion coefficient. We plug 4 into our equation and square it, giving us 16. Dividing this by 0.002 yields a staggering 8,000 seconds. The mathematical reasoning here is clear. Increasing the thickness by a factor of 4 increases the diffusion time by a factor of 16. Over 2 hours for a single molecule of oxygen to reach deep tissues is completely unsustainable, proving exactly why thicker animals absolutely require a fluid-filled coelom to circulate nutrients. This mathematical necessity brings us to the actual anatomical structures we use for classification, as shown in this diagram. You are looking at the evolutionary progression of body cavities in non-chordates. On the far left, we have the acoelomate body plan, like our flatworm, where the space between the gut and the outer layer is completely filled with solid tissue. In the middle is the pseudocoelomate, which has evolved a simple cavity between the inner and middle tissue layers to help circulate fluids. Finally, on the right, we see the eucoelomate, possessing a true coelom entirely enclosed within the middle tissue layer. This diagram visually summarizes how animals evolved internal spaces to overcome the physical limits of diffusion. As we wrap up, let us reinforce the most important ideas from this topic. First, the basis of classification is the essential framework that brings order to the immense diversity of the animal kingdom by looking at fundamental body blueprints. Second, we classify non-chordates using key traits like cellular organization, body symmetry, and the presence of a column. Finally, as we proved mathematically, these anatomical features are not arbitrary. They are brilliant evolutionary solutions to physical problems like surface area and diffusion limits. You now have a solid understanding of how life evolved from simple protists to complex organisms.